So today we are going to study binary search tree. So in binary search tree, let us take a node n, and in this tree, in this binary search tree, every element to the left is always less than or equal to n. Okay, and to the right we have every element is greater than or equal to n. Okay, for example, I am having 10 and to the left I am having 8 and to this we have 11. We can say that the given tree is a binary search tree because to this root every element to its left is less than 10 and element to its right is greater than 10. So simply we can say that the given tree is binary search tree. Let us take few more example on this binary search tree. For example, I am having here 15, to left we have 13 and here we have 14 and 12. Okay, and here we have 16. So is this a binary tree or not? Let us check. Start with this leaf node. 12 is okay because it having no node. 14 is okay. So we can say that here the condition is all okay. Now I will check here. So 13. So to this node 13, the elements which are to its left should be less than 13 or equal to 13. So here it is true for the binary search tree, and to the right every element should be greater than 13. So it is okay for that to be a binary search tree up to here. Now we will take at node 15, or we will check at node 15. So 15, every element to the left, which is this side, is less than 15. Okay, 13 is less than 15, 12 is also, and 14 is also less than 15. Okay, then left side is okay, and to the right, that is only one element, it is 16, and 16 is greater than 15. So condition is okay, so we can say that the given tree is binary search tree. Okay, but if I will add an element here 17, okay, so the given tree is not a binary search tree because 17 is getting problem here, because 17 I have to insert it here instead of here. So with this the given tree is not binary search tree because 17 is greater than 15, then it will come to the this side, and again it will come to this side of 16. Okay, so this is not binary search tree. Okay, so here's few problems with binary search tree. If I am getting elements like this 11, then I am getting 10, then I am getting 9. So in this type of binary search tree, there is a problem with the height of the tree. So for solving the problem of height, we introduce AVL trees. Okay, so AVL tree is further extension of binary search tree with balance factor. Okay, for example, AVL tree. Okay, so we can say that AVL tree is a binary search tree. BST means binary search tree with balance factor. Balance factor. Okay. Now what is this balance factor? Let us understand this balance factor with an example. Okay. So suppose I am having a tree in which elements are 14, 12 and 15. Okay. First, balance factor. So what is the height of that given tree? So at this point height is 0. At this point height is 0. At this point height is again 0. So how to calculate that height? So height can be calculated by, or before calculating height I will explain you balance factor. So balance factor is equivalent to height of left minus height of right. Okay. So with this formula I can calculate the balance factor. So now how to calculate the balance factor? I am writing this example here. 14, 12 and 14, 12 and 15. Okay. So how to calculate the height? Suppose this tree level 0 and this one is the level 1, and I am again expanding the given tree 13 and 10. Okay, and this one is the level 2. Okay, so for calculating the height of this node is 0. Okay, because no further extension of the nodes. Here is also height 0, and here height is 1, and here at this node height is 2, because first level is this one and second is this one. So we can say that height is 2. Okay, so at this level height of this node is 0. Okay, so how to calculate the balance factor? In the following tree is, as we have discussed, the balance factor is height of the left minus height of the right. So first I will calculate the balance factor here. So balance factor at this node is 0, because to its left there is no node and to its right there is no node. So 0 minus 0 is equal to 0. Here same case, 0 minus 0 is equal to 0. So here is the case of interest. Okay, at this node balance factor will be, what is the height of left? It is 1, because here is 1 level. And what is the height at right? Same, it is 1. Okay, so 1 minus 1, it is 0. Okay, so for calculating height at this node, we find the balance factor. Balance factor will be the elements to its left 0. Okay, and the element to its right is also 0. So balance factor is 0. So at this point balance factor will be elements to its left side, height of the left. So height of the left is 1 and 2. 1 level, first level, and this one is the second level. So we can say that 2, which is left side, and the height of the right is 1, because there is only 1 level. So balance factor here is 1. Okay, this is how we can calculate the balance factor. So in AVL tree, I have to maintain the balance factor either 0 or -1 or +1. Okay, I'm repeating here, the balance factor in an AVL tree should be either 0, -1 or +1. For example, if I am taking a tree like this, A, B, C. So the balance factor here is 0. Here balance factor is 0. Same here, 1 minus 1, because 1 to left is 1 and to right is also 1 and it is 0. So here balance factor is 0, 0, 0, then it is okay for the AVL tree. But if I am taking a case in which I am having 10, 9 and 8, okay, so balance factor at this level is 0 minus 0, 0 minus 0, which is 0, and balance factor at this level is 1, because the left height is 1 and the right there is no, so 1 minus 0, which is 1, then it is okay up to this level. And for finding the height at this level or the balance factor at this level is, what is the balance factor here? The height of left is 1 and 2, so 2, and to the right we have nothing, so balance factor here is 2. Okay, so here is a problem. Okay, so we cannot say we can't say that the given tree, this one tree is an AVL tree. Okay, because the height at this level is 2 and we have to maintain the height between 0, -1 or +1. So if I am getting a problem with the balance factor, then we have rotations in AVL tree. Okay, so we have, if I am getting the problem with the balance factor, or I can say that if I am getting a balance factor 2 or more than +1, which is 2, 3 or something more than 1, then we have to balance or we have to apply rotations to that AVL tree. Okay, and the rotations are, we have 4 types of rotations. Okay, the first is LL, or we can say that left, left, and second one type of rotation is RR, means right, right, and third type of rotation we have RL, or we can say that right, left, and fourth type of rotation we have left, right. Okay, so let us understand the first, that is LL. Okay, so let us understand that LL rotation with the help of example. So let us take, I am having a tree like this. So here BF is here elements are 3, 2 and 1. So here balance factor is 0 minus 0, which is 0. Here balance factor is 1 minus 0, because left side we have height 1 and to right 0, so balance factor is 1. But here is problem, the balance factor is 1 2 which is left, 2 minus 0 which is 2. So here is the problem. So we apply and the problem is due to its left side. Okay, so if I am getting this problem of height here, so I will apply the rotation LL. Okay, these are the rotations. So I will apply the rotation LL. So in LL rotation, I will rotate the elements to the clockwise. This element to the clockwise. If I am 2 3, then I will rotate this element like this. Okay, for example, I am having 2 1 and here 3, but I will rotate this element clockwise. This become this. Okay, so after L, we can say that clockwise. This is the case of left rotation. And in second case, which is right rotation, in which for example, in which I am getting okay, so here this is the right side of a tree and this is the right side of a tree. So the problem is, what is the balance factor here? BF will be, right is 0 and left is 0. So here, what will the balance factor? Balance factor will be, balance factor here, I will put the balance factor to the this side. Okay, so balance factor will be 0, and here, but what is the balance factor? Balance factor will be the element to its left, which is 0, and to right is -1. So balance factor is -1, and it is okay for the AVL tree. But here the BF will be 0 because right side 0 element, and to the right, to the left we have 0 element, to the right we have 2 element. Height is 2. So but is the balance factor 0 minus 2, which is -2. Okay, so here is problem. So if I am getting this type of RR issue, so I will apply the RR rotation. So after applying, I will apply the RR rotation here, RR instead of here. So after applying the RR rotation, I will rotate the elements to this element to the anti-clockwise. Okay, like this. Okay, like this. So the resultant after I will get 2. I will apply here 1 and 3. Okay, so here BF is equal to 0, BF is equal to 0, and here BF is equal to 0. So all okay for that. Okay, and rotation is anti-clockwise. Okay, so this is the case of RR rotation. The next case is RL rotation. So in this case of RL rotation, let us take an example in which we have elements 1, 3 and 2. Okay, so here balance factor is 0, here balance factor is to left 1 minus to right 0, which is 1, and here balance factor is to right to left is nothing, which is 0, and right we have two heights, which is 1 and 2. So we can say that 2. So balance factor is -2. So here is problem for the AVL tree. So I will apply, and problem is due to right and left. Right and left. So I will apply the RL rotation, and RL rotation is a combination of, first we will apply left left, first we will apply left left, plus then we will apply right right. Okay, so apply the so first, so in our allocation, first we will apply the left left. Okay, so by applying the left left rotation, I will rotate the elements, like this element I will rotate this to this type. Okay, this one I am repeating here, means after applying, first I will rotate 2 to here and 3 to here, and resultant will become 1, 2 will come here and 3 will come to down. Okay, so this is first apply LL, then to this side I will apply the right right, because second I have to apply right right rotation. So after applying right right rotation, I have to move anti-clockwise like this. The resultant tree will become 1 and 3. Okay, this is 1. Okay, so this is the resultant. So we can say that RL rotation is the combination of first LL, and after LL we have to apply RR. Okay, so next we will look at LR rotations. So in this case of LR rotation, I am having 3, then I am having 1, and here 2. Okay, so at this balance factor is 0, at this balance factor is